Dynamic equalizing capacitor. Okay, in last class we discussed SCR operation, applications, and characteristics and series operation. Okay, today we will discuss dynamic equalizing capacitor. Okay, so in dynamic equalizing capacitor. So the dynamic equalizing capacitor, the thyristors, why you want to study dynamic equalizing capacitor means, so you have to you have to connect the thyristor in parallel operation. By using capacitor we can connect the thyristor in parallel operation. Okay, so considering the dynamic characteristics of SCR, so these are the dynamic equalizing so we are connecting capacitor parallel to thyristor. So this is capacitor is called dynamic equalizing capacitor. So these two thyristors will be connected in parallel with the help of dynamic equalizing capacitors. Okay. So if you want to calculate capacitor, then if you want to calculate capacitor, so when you are connecting parallel in thyristor, okay, so voltage across the first tap of thyristor will be, so for voltage across the first tap of thyristor V1 equal to VBM. Okay, voltage across the first tap of thyristor will V1 equal to VBM. Voltage across the second bottom. So this second thyristor V2 equal to VB, voltage equal to VBM minus delta Q by C. Okay, so where delta Q equal to charge in capacitor to and charging in capacitor minus charging in capacitor. Okay, so the V2 will be the V2 will be calculated. So first capacitor voltage minus total change in charge in two capacitors by 2 by capacitor. Okay, so where delta Q equal to QT minus Q1. So the voltage will be, the voltage total voltage equal to V1 plus V2. So V1 equal to VBM plus V2 equal to VBM minus delta Q by C. So voltage across the N minus 1 slow thyristors equal to N minus 1 into V. So V2. So N minus 1 into V2 means VBM minus delta Q by C. So here voltage, total voltage equal to V1 plus N minus 1 into V2. So Vs equal to V1 plus N minus 1 into V2 means VBM minus delta Q by C. So first simplification, it's simplified, then VBM equal to 1 by N Bs minus N minus 1 into delta Q by C. So from this we have calculated capacitor equal to VBM minus 1 delta Q by N VBM minus Vs. So by using dynamic equalizing capacitor, we are calculating a capacitor. Okay. So next, parallel operations of SCR. So we are connecting parallel operation. So in parallel, the voltage will be same, the current will be depreciated. Okay, so the current in thyristor 1 I1 and current in thyristor 2 will be I2. So when you draw a graph between the voltage and current, the graph will be flows like this. So the current in thyristor 1 will be goes on increasing, and current in thyristor 2 will also goes on increasing. So for unsymmetrical mounting, the the holes are electrons will be located with this manner. For symmetrical mountain, the holes and electrons are mounted in this manner. Okay, next some problem, I have given two example problems. Okay, SCR ratings of 1000 volts and 200 volts, okay, are available to be used in string to handle 6 kV and 11 kV. Okay, calculate the number of series and parallel units required. You, in case of derating factor A equal to 0.1 and 0.2. So here SCR ratings are given 1000 volts and 200 volts. So these two SCRs, so these SCRs will be used to handle a string of 16 kV and 11 kV. So you have to calculate number of series and parallel units required. Okay, so here derating factor are given. So derating factor equal to 1 minus string efficiency. So string efficiency equal to string voltage by total number of so here number of string. So total number of string thyristors ns and rating of voltage. Okay, so in case 1 derating factor equal to 0.1. So derating factor 0.1 equal to 1 minus, here string efficiency means uh, string voltage and the 600. Here you have to given 16 kV ante 6 into 10 power cube. So total 6000 by ns into 100. So 6000 by ns into 100 equal to 1 minus 0. So ns equal to 6000 by 0.9 into 1000. Okay, so 6.6 into 7. So series thyristors SCRs are required will be 7. Okay, so by using derating factor and string efficiency, we can calculate how many parallel and series thyristors will be required. Okay, derating factor equal to 1 minus string efficiency. Okay, so in string efficiency equal to string current by, so we have here we are calculated series thyristor, and when we calculate parallel thyristor, so in parallel the parallel means current will be different. So string current will be 1000 100 means 1 kV, that means 1000 by number of parallel thyristors into rating of a current. So derating factor will be here 0.1. So in first case 0.1 we have to calculate series thyristors and parallel thyristors. Okay, so here derating factor will be 0.1. So 0.1 equal to 1 minus string efficiency. String efficiency will be string current how much? 1000 by number of parallel connected thyristors into rating of a rating of a thyristor current 200. So we have simplifying this. So parallel thyristors SCRs are required is will be obtained 6. Okay, so next, static characteristics of SCR. So static characteristics also called VI characteristics. So an elementary circuit diagram obtaining a static VI characteristics of thyristor is are connected to main source through a load. So here the SCR, so elementary circuit diagram will be given. So this is anode and this is cathode. So on gate, so gate we have applied input and load. So these are the varying load. Okay, so the load will be varied. So here anode and cathode are connected to main source. So this anode and cathode connected to here main source. Okay, through a load. So by using through a load, we are connected anode and cathode to a main source. The gate and cathode are fed from another source is EG. So this gate and this cathode will be fed another source EG. Okay. So the static VI characteristics of SCR is shown in figure 2. Here VA is the anode. Here VA is the anode cathode voltage. So here apply here we are calculated voltage will be anode cathode voltage. Okay, so voltage and IA is the anode. Here the current flowing in this circuit, it will be IA is the anode current. The thyristor VI characteristics is divided into 3 regions. This region of operations is described. So the characteristics of operation and thyristor operations will be in three modes. So thyristor conduction, thyristor forward blocking mode and forward conduction mode and reverse blocking mode. So these three will be in VI characteristics. Okay. Already we discussed SCR VI characteristics. Na? So that will be static characteristics. Okay. So these are the VI characteristics. So we are taking the forward voltage on x-axis and current on y-axis. So at first the thyristor will not conduct, so the leakage current will be flowing in forward blocking region, and the after when you applying gate input, the current will be conducted, so the and high current will be flowing in forward conduction mode. Okay. In reverse blocking mode, there is no current flowing. So only leakage current will be flowing. Whenever reverse avalanche is then applied, then the current will be in reverse direction also will flow. Okay. So reverse blocking region. When the cathode is made positive with respect to anode with the switch S is open, the thyristor become blocking region. So in this region, thyristor exhibit blocking characteristics similar to the outer junction. So in reverse blocking, so we have discussed in this circuit. So in reverse blocking region, so first reverse blocking region you have discussing. So in reverse blocking region, when we are applying a negative source to anode and positive source to cathode, and there is no input given to there is no input given to gate, then only reverse leakage current flowing from cathode to anode or anode to cathode. Okay. So there is no current flowing from anode to cathode in reverse blocking region, so that's why there is no current flowing. Okay. So whenever there is no current flowing, so thyristor will have three junctions, already we discussed now. So J1 and G3 are reverse bias and the middle junction J2 is forward bias. There is only small leakage current in milliamps flows. So the reverse voltage is increased then at critical breakdown level called reverse breakdown voltage VBR. In avalanche will be occur at J1 and J3 increasing the current. Okay. Increasing the current sharply in this current, it is not limited to a safe value. Power dissipation will be increased to a dangerous level that may be destroy the device region PQ. So in the reverse avalanche region, in this reverse voltage applied across the device is below the critical value. So the device will behave as a high impedance device essentially in the reverse direction. The inner two regions of SCR are lightly doped. So the inner so J2 is depreciated and leaded during the forward bias condition will be greater than the total thickness of two depletion layer at J1 and J3. When the device is reverse bias, therefore the forward breakdown voltage VB0 is generally higher than the reverse breakdown voltage. Okay. So next forward blocking region. In this region, the anode is made positive with respect to the cathode. With respect to the cathode, and therefore junction J1 and J3 are reverse bias. Hence, anode current is a small forward leakage current. The region OM of the VI characteristics is shown in forward blocking region. So the device does not connect. So in forward conduction region, when the anode cathode forward voltage is increased with the gate circuit kept in open, avalanche breakdown occur. So at the junction J2. So at critical forward breakdown voltage VB0 and the SCR switches into low impedance conduction. Okay. So forward breaker over voltage corresponding to a point M, the device launches into conduction. So as soon as the device launches into its on state, the voltage across the device drops from this several hundred volts, 12 volts, depending upon the rating of SCR. So so current flowing through device. So the part of the characteristics is called the forward conduction state. So these are the forward conduction region. And so here in graph we have to see static VI characteristics. So here this is the forward blocking region, and this is the forward conduction region, and this is the reverse blocking region and reverse avalanche region. So at first the leakage current will be flowing whenever gate input will be given, then only thyristor will be conduct. So this is forward conduction region. So in reverse blocking region, there is leakage current first flowing. Whenever reverse avalanche region will be applied, then reverse current will be flowing. Okay. So these are the static VI characteristics. Next will be triggering method. So why you have to use triggering method means thyristor turning on is also known as triggering. With the anode positive with respect to cathode, a thyristor can be turned on by by any one of the following techniques. So triggering method means the thyristor will be turned on by using these methods. So forward voltage triggering, gate triggering, dV by dt triggering, temperature triggering, and light triggering. Okay. So first, forward voltage triggering. When the breaker voltage VBO across the thyristor is exceeded, then the rated maximum voltage of the device. So thyristor will be turned on. At the breaker voltage, the value of thyristor anode current is called as latching current. So at the breaker voltage, the value of thyristor anode current is called as latching current. Breakover voltage triggering is not normally used as a triggering method, and the most circuit design attempts to avoid its occurrence. Okay. When the thyristor is triggered by exceeding VBO, the fall time of forward voltage is quite low. Okay. However, a thyristor switches faster with VBO turn on than with the gate turn on. So permitted di by dt breakover voltage turn on is slower. So forward voltage triggering means from anode to cathode. So in SCR, from anode to cathode, we are increasing the voltage, then will be thyristor will be turned on. This is the forward voltage triggering. So at forward voltage triggering, the breakover voltage, the value of thyristor anode current. So at forward, we are increasing from anode to cathode voltage. Then current will be flowing at that time. That is called latching current. Okay. So next dV by dt. So with the forward voltage across the anode and cathode of thyristor, two outer junctions A and C are forward bias, but the inner junction J2 is reverse bias. So the reverse bias junction J2 behaves like a capacitor because of the space charge present there. So as PN junction has a capacitance, so larger the junction area, so larger the capacitance. If the voltage ramp is applied across the anode to cathode, a current will be flow in the device. So to charge the device capacitance according to the relaxation. So if the charging occur, IC equal to C into dV by dt. Large enough density of moving current carries in the device induces switch on. This method of triggering is not desirable because of high charging current. IC may be damage the thyristor. So dV by dt triggering means at first J2 behaves as a capacitor. Then only so PN junction has a capacitance. So larger the junction area, the larger the capacitance. So the voltage ramp is applied across the anode to cathode. Current will flow in the device charge. The device capacitance according to relaxation. So we have charging currency IC equal to C into dV by dt. Large enough density of moving current carries in the device introduce the switching on. So the method of this dV by dt method also danger to the thyristor. Next triggering will be temperature triggering. During forward blocking, most of the applied voltage appears across the reverse bias junction J2. So this voltage across J2 associated with a may rise the temperature of this junction. With the increasing in temperature, leakage current through a junction J2 further increases. This cumulative process may be turned on the SCR at some high temperature. High temperature triggering may cause thermal runaway and generally avoided. So at J2 associated with leakage current may rise the temperature of your junction. So in reverse bias junction, the leakage current may rise the temperature of this junction. So with increasing the temperature, leakage current through a junction J2 further increases. This cumulative process may be turned on the SCR. Okay, at some high temperature. Okay. Next will be light triggering. In this method, light particles, a light particle means photons are made to strike the reverse biased junction, which cause an increasing in the number of electron hole pairs and triggering of the thyristor. So we have see anode cathode. So here P type J1 and J3, J1, J2, J3 are junctions. Whenever we are applying light photon to P diode. So the for a light triggered SR is slot is made with a inner P layer when it is irradiated free charge. Free charge carriers are generated just like when gate signal is applied between the gate and cathode. Okay. So pulse light of appropriate wavelength is guided by an optical fiber for irradiation. In the intensity of a light thrown on the recess exceeds the certain level, certain value. Forward biased SCR is turned on. Such a thyristor is known as light activated SCR. So light triggered thyristor is mostly used in high voltage direct current. So transmission system. So in light triggering method, we have applying here in P layer. So when photons will be applied in P layer, so this will be same as when voltage applying gate to cathode. Okay. So light triggering method is mostly used in HVDC transmission system. So next will be thyristor gate control method. So thyristor gate control method means an easy method of switch on the SCR into conduction is to apply the proper positive signal to good. So by applying positive signal to gate, the SCR will be turned on in this method. So this signal should be applied when the thyristor is forward biased and should be removed after the device has been switched on. Thyristor turn on time should be range of 1 to 4 microseconds, while turn off time must be between 8 to 50 microseconds. So thyristor gate signal can be in three varieties: DC gate signal, AC gate signal, and pulse. Okay. So in thyristor gate control method, DC gate signal. Application of DC gate signal causes the flow of gate current, which triggers the SCR. So disadvantage is in that gate signal has to be continuously applied, resulting in a power loss. So gate control circuit is also not isolated from the main power circuit and AC gate signal. So in this method, phase shifted AC voltage derived from the main supplies the gate signal. Instant of firing can be controlled by a phase angle control of the gate signal. And next, pulse. Here the SCR is triggered by the application of positive pulse for a current magnitude. For a thyristor, it is important to switch it on the proper instant certain sequence. So this can be done by a train of high frequency pulses at a proper instant through a logic circuit. Pulse transformer is used for a circuit isolation. Here the gate losses are very low because of a drive is discontinuous. Okay. So next will be thyristor commutation. So process of turning off a conducting thyristor. So this will be discussed in next class. Okay. So today we will discuss the parallel operation of thyristor and triggering methods, static VI characteristics of thyristor and triggering method. So triggering method means turning on the thyristor. So turning on the thyristor means the SCR will be turned on by using these methods: forward voltage triggering, gate triggering, TV by DT triggering, and temperature triggering, light triggering. In forward voltage triggering means the voltage will be applied from anode to cathode, will be increasing. And gate triggering means whenever we are applying gate input. So and dv by dt triggering means in reverse bias the leakage current will be, so in dv by dt, so dv by dt triggering means so in reverse bias junction J2, so J2 behaves like a capacitor. So by calculating the charging current, so we can we can turning on the thyristor. Next, temperature triggering means so in reverse leakage current some temperature loss will be there. So by increasing temperature loss, by increasing the reverse leakage current, then the SCR will be irritating. So light triggering means here in light triggering we have using photons. So by applying photons in p layer, hmm, then thyristor will be turned on. So thyristor will be turned on by using light triggering is used in HVDC transmission system. Okay, this is our class. Okay.